Dr. S. Kohila, Assistant Professor, Department of Mathematics, VV Vanniya Perumal College for Women. In this session, I am going to take a topic on cyclic groups. A group G is said to be cyclic if there exists an element A belongs to G such that every element of G is an integral power of A. Example, the additive group Z5 which contains 5 elements from 0, 1, 2, 3, 4. This additive group is cyclic. And another one example, the multiplicative group 5 is also cyclic, which means every element can be written in the generator of this group. Look at some examples. A group G equal to 1, minus 1, I, minus I is a cyclic group under the product, which means the generators are I and minus I. How to prove this group is cyclic group? The group G equal to 1, minus 1, I, minus I is a cyclic group. How can you say this group is cyclic group? Which means here the generators are I and minus I. Generator means with the use of these elements we can generate all the elements of this group. Here I is one of the element. Next I square equal to minus 1. Minus 1 is also one of the element in this group. Next I cube, which means I square into I, that is minus 1 into I, that is minus I. Minus I is also one of the group. Here I minus 1, then minus I. 3 elements comes with the use of the generator I, and I power 4. I power 4 is I square into I square, that is minus 1 into minus 1, 1. So the first element and the second element, third element and fourth element, all the elements of the groups can be obtained from the generator element I. Similarly, we can derive the element minus I is also the generator of this group G equal to 1, minus 1, I, minus I. In this way we can find the elements. For example, minus I power 1, that is minus I, then minus I the whole square, that is minus I into minus I, we are getting plus I, then minus I the whole cube, that is minus I the whole square into minus I, that is minus I into minus I, plus I into minus I, then minus I the whole power 4, we are getting the element 1. This is a good example for cyclic group. Next example, 1 omega square is a cyclic group with the generators omega and omega square. Here also the generators are omega and omega square. We know that omega cube equal to 1. We know that omega cube equal to 1. Then omega power 4 is omega cube into omega, that is 1 into omega. This is a second element of this group. Then omega square can be written as omega square. This is also one of the element. So the group contains 3 elements, 1, omega and omega square. Omega square is the generator, means omega square is one of the element in this group. Then omega cube is 1. Omega cube equal to 1 is also one of the element. Then omega power 4 is omega is the result. So omega is also one of the element. Therefore omega square is a generator of this group, G. Next example, Zn, additive group of n is also a cyclic group for every n. Zn is the set of integers, that is Z5 means the elements of this group is 0, 1, 2, 3, 4. This is also a cyclic group, that is 0 plus 1, 1 is one of the element. Then 2 plus 1, 3, 3 is also one of the element. Likewise, we can derive all those elements of this particular group. Then nz comma plus is a cyclic group with generator n and minus n. For every integer, we can derive all those elements in that corresponding group. The last one is z comma plus, that is set of integers under the operation addition is a cyclic group with the generator 1 and minus 1. In this cyclic group, n value is 1. Similarly, we can find 2z comma plus is a cyclic group and 3z comma plus is also a cyclic group. U of 8 means, that is pi of 8. Pi of 8 means Euler's theorem says, that is what all the elements are less than n and relatively prime to n, that is called the pi of n. Here pi of 8, what all the elements under the, that is less than 8 are 1, 3, 5, 7. These are all the elements less than 8 and relatively prime to 8. That's what we can say, that pi of 8 equal to 4. And u of 8 means how many elements are comes in pi of n. Here 4 elements. This is not cyclic because 5 and 7 cannot be generated by any element of this group. That's what this u of 8 is not cyclic. Next example, q of plus is not cyclic group. Similarly, r comma plus is also a cyclic group. Q of plus is not a cyclic group and r comma plus is a cyclic group. We can check it. Next, some of the results under the cyclic group. Every subgroup of a cyclic group is cyclic if cyclic group equal to n. Then the order of any subgroup of the cyclic group A is a divisor of n. Order of any subgroup of the cyclic group A is a divisor of n. Next result is a subgroup of an abelian group is abelian. If A is a generator of a cyclic group, then the inverse of A is also its generator. If A is a generator, then inverse of A is also a generator of the same group. Before that, we have seen one example. G equal to 1 comma minus 1 comma I comma minus I. In this group, I is a generator of this group G. Similarly, minus I is also a generator of this group. So, this statement is true. The order of a cyclic group is order of its generator, which means order of a cyclic group. In the previous example, order of a cyclic group is 4. Then order of its generator, that is generator here I and minus I in this previous example. The generator order is equal to the order of a group, that is I generator order is 4 and minus I generator, minus I is also a generator, this order is also 4. So, we can say order of a cyclic group is equal to order of its generator. Next, every cyclic group is abelian, but an abelian group need not be cyclic. It's universal truth. Every cyclic group is abelian, but abelian group need not be cyclic. Every group of prime order is cyclic. It's very important concept. Every group of prime order is cyclic. In case your group order is 3, 5, 7 like this, immediately we can say the group is cyclic. Every group of order 11 is abelian and cyclic. Every group of order 11 is abelian and cyclic. If a group of order is 11 is, immediately you can say that group is abelian and cyclic. Then every group of order 4 is abelian but not cyclic. In the previous statement is, if the group of order is 11 means we can say both abelian and cyclic, but the group of order 4 means it is abelian but need not be cyclic. The best example is Klein group. Klein group order is 4. It is abelian but not cyclic. The next result is, if a cyclic group is generated by an element A of order n, then A power m is a generator if GCD of m comma n equal to 1. If a cyclic group is generated by an element A of order n, that is GCD of m comma n is n 1. G is a cyclic group 1 comma minus 1 comma I comma minus I. We can take the same example. I is a generator of order 4. Then m is 1. Then the GCD of 1 comma 4 is equal to 1. In this statement, generated by an element A of order n, then A power m is a generator if GCD of A is a of order n. I is a generator of order 4. Then I power 1 is also a generator. That is, I is also a generator when GCD of m comma n. Here m value is 1 and 4 is order of A. Then GCD of 1 comma 4 equal to 1. So I is also a generator, I power 4 is also a generator. Next statement, if order of G equal to P square, then G is abelian but need not be cyclic. Which means order of G equal to 3 square. 3 is a prime number, 3 square. Order of G equal to 9 is abelian but need not be cyclic.